Alrighty, good morning, everyone. It is my pleasure to introduce today's speaker, Dr. Joao Teixeira, a leading atmospheric scientist who has made significant contributions in the area of turbulence, clouds, and climate. Dr. Teixeira is a principal scientist at NASA's Jet Propulsion Laboratory and has been serving as co-director of the JPL Center for Climate Sciences and is a science team leader for the Atmospheric Infrared Sounder, or AIRS mission. His research bridges small-scale processes such as turbulence and convection with large-scale dynamics to improve how we model and predict our changing atmosphere. He earned his PhD in meteorology from the University of Lisbon and has held key positions in prestigious institutions, including the European Center for Medium-Range Weather Forecasts, the Naval Research Laboratory, and NATO's Undersea Research Center. So please join me in welcoming Dr. Joao Teixeira. Please take it away.
Thank you, Peter. Thank you for the nice introduction. Thank you very much. Thank you so much for the invitation. It's a real pleasure. This is, of course, work done by a ton of people. I chose to highlight my colleagues, Maria Shinita, Kai Susha, Alan Harrington, Marcin Kurowski, and Chenan Zhang, who have worked closely with me over the last almost 15 years, some of them. And we are distributed across different groups. We have a team. Most of us are at the Jet Propulsion Laboratory and have affiliations with University of California, LA. And Adam is at National Center for Atmospheric Research. A lot of this research that I'm going to show has been funded by NASA, by the Department of Energy, and recently, over the last 5 years, by a CPT grant from the National Science Foundation. ONR and NOAA have funded previous efforts as well. So let me just try to introduce the problem very quickly. And again, if I'm speaking and the slides haven't shown, let me know. So work on atmospheric modeling, so you know a lot of these things very well. So I'll be brief on my introduction, but the point of this slide is really to highlight the fact that, on the one hand, the atmosphere is a very turbulent flow or fluid, depending on how you want to call it, it's both, where in particular mixed phase physics and radiative transfer, both long wave and short wave, play an essential role, both for weather and climate, as you know, precipitation on weather, for example, or cloud radiation interaction for climate. Now, it turns out that in current models, both for weather and climate, and what I'm going to talk about applies to both weather and climate models. It's essentially about global atmospheric models. They tend to be very similar, as most of you know this very well. But often what we have is that the parameterizations to represent some of these physical processes, and in particular to represent mixing processes like turbulence and convection, tend to be very modular. The reason is historical and cultural, because a lot of our tools that we develop are engineering tools, so we often tend to be pragmatic. So even before we have better theories or better approaches, we go and code things and make them work. So this is a schematic that I think something similar, Arakawa had the first schematic similar to this, and I think Bjorn Stevens did it, and then a few others, and ended up at the IPCC AR5. That's the version. And let's imagine this is a cross-section from, let's say, California to the ITCZ, and you can see that you go from sort of dry boundary layers to stratocumulus, shallow convection, and deep convection. And I hope you can see my cursor. And it turns out that, as I mentioned, often parameterizations are so modular that, for example, when I was at ECMWF in the 90s, and I think it's still partly true to a certain extent, we would have a routine that does a stratocumulus mixing, another routine that does shallow convection, another one does the dry PBL, and so on. And really, that modularity presents a variety of challenges, not only sort of theoretical challenges, but also very practical challenges, because you have to abruptly change from one regime to the other, and those sort of decisions are often very arbitrary. So a goal of our research group, and some others, has been to try to come up with sort of more unified or more integrated parameterizations for turbulence, convection, and cloud macrophysics, to be able to represent with one single approach all of the different manifestations of turbulence in the atmosphere. Now, again, you all know this, global atmospheric models are essentially three-dimensional, large-scale dynamic models with one-dimensional physics, column physics. They vary in sort of horizontal resolution. The National Weather Service or ECMWF global weather prediction models have resolutions of about 10 by 10 kilometers. Climate models will be between 50 by 50, 50 by 100 by 100 kilometers. The most recent efforts in sort of global cloud resolving model take us to about 3 kilometers resolution. So in any case, even if you go to 10 kilometers, even if you go to 3 kilometers, a lot of what happens in terms of clouds, for example, is subgrid scale. Right? I mean, you just need to look outside the window and realize that clouds are not just boxes of 100 by 100 kilometers, that there's a lot of small scale variability and small scale physics that, because the atmosphere is a nonlinear flow, does affect the large scale. So whatever happens at the small scales can have a huge impact on the large scales, and that's why we're worried about this problem. Now, I'm not going to spend a lot of time writing a lot of complex partial differential equations, but this one is a simple example of, let's say, a scalar flow, or the equation that rules the balance of a scalar in the atmosphere with a source and sink, which I put on called S just to simplify it. And often the way people look at this and try to handle the small scales is by assuming that we have an inherent and implicit PDF of these properties in the box. And as such, then the value of a particular variable of a particular scalar is going to be its mean plus a perturbation. And if you actually do this Reynolds decomposition and you do averaging again, we end up with an equation that is very similar to this in general. You will have an Eulerian tendency for the mean, a mean advection, so that term over here on the left-hand side as well. And then on the right-hand side, for the atmosphere, if we basically amalgamate all of the kind of sources and sinks on the right-hand side and don't worry about it for the moment, we have a remaining term, which is this vertical divergence of this covariance. This is the covariance between the vertical velocity and the scalar. It could be a temperature, it could be a water variable. And so this, let's call it subgrid scale flux, the divergence of this subgrid scale flux is really at the heart of the turbulence and convection parameterization problem. So you could argue in a simple way that trying to find out what the right equations are for this covariance is the way to solve the turbulence and convection parameterization problem in an atmospheric model. This applies to ocean models and other fluids, of course, as well, in slightly different constraints. Now, I'll digress for like 30 seconds to mention something which is kind of the bread and butter of a lot of what we do, which is to develop and use large eddy simulation models. And they play a fundamental role in helping us understand how turbulence and convection operates, but also plays a fundamental role as sort of a validation tool, as sort of the ground truth that we compare our parameterizations and our sort of large-scale models to. LES models are nothing else than versions of Navier-Stokes. The reason why they are particularly important in this case is that we tend to run them in small domains, so let's say 20 by 20 kilometers, and because of that, we can use very high resolution. So we don't have to cover the entire globe, so we're not constrained by the size of the domain. We can make it as small as necessary to study a particular problem. And of course, closures are still needed for scalars smaller than the grid box, let's say 10 by 10 meters. But it's much simpler as a problem than GCMs. And LES are extremely realistic, as you can see from this image. You would be hard pressed to distinguish this from a photograph from an airplane, except for maybe the surface being too smooth. So we use LES a lot. Let me go back to the covariance that we're talking about, right? The subgrid scale flux. Now, historically, which assumes that this covariance, this subgrid scale flux, is proportional to a gradient, is an approach that has been used in turbulence research and turbulence modeling from the beginnings of modern studies of turbulence. So Reynolds, and even before that, Saint-Venant and Bouzinès proposed eddy diffusivity as an approach to represent turbulence. Mass flux is another approach that, I'll show you a slide next explaining a little bit better what it is, but it's associated with the idea of a plume and how plumes mix in the atmosphere. And its origins are from papers in the 40s and the 50s. And in the US, by Stommel, by Simpson, and others. Now, turns out that if you actually divide a grid box of a model in two regions, let's say a region that's going up, an updraft, and a region that is going down, an environment or a downdraft, or you can call it other things, and then you do Reynolds decomposition and averaging, you end up with a term that is a little bit more complex, which is that this subgrid scale flux is basically a combination of three terms. The first term is basically the amount of turbulence that exists inside the updraft. So AU is the updraft area, so it's something between 0 and 1 within the grid box. The second term, which is 1 minus AU, is really the turbulence that exists in the environment, in the regions around this updraft, around this plume. And the last term is a critical one, which is essentially about the exchange of properties between the updrafts and the environment. Now, an approach that we've used, or a simplification that we've used, and many people have used, of course, since basically mass flux approaches have been around, but we don't use it exactly in this way anymore. But from a pedagogical perspective, it's interesting to look at, is to assume that the updraft area is really much, much, much smaller than one. In that sense, you can ignore the terms that multiply by a u, and you end up with an equation in which your sort of subgrid scale flux is really two components. One, the turbulence that exists in the environment around the updrafts, and the second term that is what we call the mass flux term, which is about, again, sort of the interactions between the mixing that happens between the updraft and the environment. And about 25 years ago now, Pierre Sibisman and I were working on this, and we decided to assume that, why don't we assume that you use eddy diffusivity closure for the first one, you use this sort of mass flux approximation for the second one, we solve it all together, so it's not that you solve one first and the other one much later in your code, but really have it that is completely sort of integrated from the equation perspective, the algorithm perspective, the code perspective. You end up with an integrated or unified parameterization of different turbulence and convection scales. So in which the eddy diffusivity is dealing with the small scales and the convection is dealt by the mass flux. And in the next slide, you can see in this schematic over here, so the idea would be, so this would be shallow convection, you would be that basically the mass flux component of EDMF represents this sort of deeper plumes that sort of scale with the depth of the boundary layer or with the troposphere for deep convection, while the diffusivity would represent the sort of the turbulence that exists in the environment around. Now, the mass flux approximation in a very simplified form basically it can be stated as this, in which the vertical flux is proportional to the mass flux term, which is the updraft area times the vertical velocity of the updraft, times the difference between, let's say, the temperature in the updraft and the mean temperature. And the way to solve this problem, to calculate what is required to close the problem, which is the mass flux term and let's say, the scalars in the updraft regions. What you do is you integrate over the plume area. If you assume steady state to simplify and you neglect some sources and sinks, you end up with rather simple equations like the ones below, in which in the first one, you can see that basically the vertical divergence or the vertical gradient of the updraft properties is just a sort of a relaxation term. It's proportional to the difference between the properties of the updraft and the mean, weighted by a particularly important term, which is the lateral entrainment rate, which basically dictates how much mixing is there between the updraft and the environment. And for the vertical velocity, the equation below, it's a little bit more complex, but it's a very similar equation, in which you have a source term that is associated with buoyancy production, and then you have a dissipation term that is not too different from the one above. Now, over the last 15 years or so, our group at JPL and at UCLA have been working on a particular version of EDMF in which we assume the existence of multiple plumes. And so by sort of parameterizing the surface layer PDF of the thermodynamic properties and by sampling that PDF to produce multiple plumes, and by also adding a stochastic lateral entrainment that was partly inspired by a work by David Roms and Jimmy Kwan, we can have a situation where you can create different types of convection that coexist in the same model grid box. And you can see that in this schematic that, one plume may actually be sampled from a more energetic part of the thermodynamics of the surface layer, and as such is, more buoyant. And that plume itself can experience less entraining events and go much further than other plumes that experience more entraining events, and as such sort of kind of die younger or shorter. And this is very important. So the idea that in the same grid box, you can have multiple different types of convection coexisting allows you to have dry convection, shallow convection, deep convection, without the need to sort of create regimes and sort of artificial transitions and things like that. They're always very risky and never really completely accurate. Now, I will just show you a couple of quick results on that. And one thing we focus a lot is on shallow convection, moist shallow convection. So this you think about, puffy popcorn clouds that you see close to Hawaii or actually in most of the subtropical oceans. This is probably the most common regime of clouds in the world, is this sort of popcorn shallow convection clouds for very, very, very large areas. In this one, we're simulating the BOMX case. We're validating against LES. We're not using our LES in this particular paper, but we're using a series of LES from an intercomparison case from a paper of, I think this is the paper of P.S. Sibisman, 2003. And so here you can see three figures. They're all profiles, the profiles of upper fraction area, upper vertical velocity, and upper liquid water content. And the LES is given in gray, and this is basically a difference between maximum and minimum of each one of the LES. There's several. There's probably about, I don't know exactly, but between 10 and 20 LES here, and gives you an idea of what sort of theoretical uncertainty we have in this case. And the different colors give you different realizations of the EDMF version that I just described briefly. And don't worry about the colors. They're not important what they signify, but what you can see is that the EDMF produces realistic thermodynamic properties, particularly because it's able to produce very realistic updraft properties. So the mean thermodynamics or the vertical fluxes, the so covariances, are very well represented. They're not here. They are in the papers. But it's essentially because we can reproduce the updraft properties in a nice way. And one way to sort of gain insight on how exactly this can be taking place and sort of make sense of it is, imagine that now you actually doing a cut on the LES horizontally. So let's say the LES is a 10 by 10 kilometer domain. You do a cut and the resolution is 10 by 10 meters. So you have many, many points from where you can collect the values of total water, which is water vapor plus liquid, and liquid water potential temperature. If you don't know exactly what liquid water potential temperature, don't worry too much about it. Think of sort of a potential temperature variable. And if you plot the LES histogram, or we call it here a joint PDF, of this total water minus the mean and the liquid water potential temperature minus the mean at a certain height at 1,000 meters above the surface, you get a distribution that looks like this, in which there's essentially two key components. One, a very probable Gaussian around the mean, so this is around the plumes. But then there's this very important, critical, skewed part of the distribution. And this is where most of the action takes place. This is where those plumes are, those puffy popcorn clouds are, and this is where the vertical mixing takes place. And you can see that the way by which, in this way of looking at the problem, the way by which the EDMF plumes actually are able to represent this mixing, you can see it here, because they basically, if you plot the properties of the EDMF plumes, and this is for a period of about half an hour, they coincide very well with the skewed part of the distribution, and they are sort of on the right part of the figure. So these multiple plumes really represent the skewed part of the PDF really realistically, and that leads to much more efficient vertical mixing, and that's why it becomes very realistic in the way it simulates shallow convection. After that, we had focused over the last few years on trying to represent the transition to deep convection. So what we're trying to do is come up with one single parameterization that can represent all different types of turbulence and convection, including deep convection. And for that, we focus on a particularly important problem and sort of difficult problem to represent, that climate and weather models even today are not very realistic in representing, which is sort of the diurnal cycle of convection over land, in particular over tropical land. This is a nice, simple schematic that François Guichard published 20 years ago. And above you have what you call explicit models, and you can think of it as LES, in which basically they represent the transition from, when sun rises, you go from a stable boundary layer to a dry convective boundary layer, then you have shallow convection, then you have like cumulus congestion, and at some stage in the evening, you have, a great episode, a very intense episode of deep convection and precipitation. And if you look at how models at the time and even today represent this from what you call the parameterizations or the single column models, so basically you can think of this as global weather and climate models, you realize that they often have a tremendous amount of difficulty in representing the timing and the amount of precipitation and the diurnal, as such, the diurnal cycle of convection over land, often creating convection, deep convection, much earlier than it should, and raining at sort of the wrong times of day, which, as you can imagine, from a forecast perspective, is not great. So what we've done with the version of EDMF that I briefly described, we added a simplified parameterizations of cloud microphysics within the plumes, simplified parameterizations of downdrafts and cold pull effects, and we are able to represent a very realistic transition from stable PBL, dry PBL, shallow and deep convection, using the EDMF multiple plume version that we've been working on. So we have a single scheme that is able to represent all these different types of convection. And you can see here, this is cloud base and cloud top. This one on the right is cumulative surface precipitation. And you can see that the cloud top is very well represented, which is a major challenge, as I will actually briefly mention later on. Now, so let me just state that we are not the only group that has been working on this. Chris Golas, Vince Larson, and their team have been working on this for a long time, from CSU to GFDL to NCAR to E3SM. Peter Bogenschutz and Steve Kruger wrote a few papers about this as well, and Caroline Lappen and Dave Randall, more or less at the same time as Chris Golas and Vince Larson, have been working on slightly different versions that haven't really been implemented. And there's other flavors around. These are not the only ones. But EDMF has been quite successful in a way, and has been implemented operationally, or at least versions of EDMF have been implemented operationally in a variety of global atmospheric models for weather prediction. So ECMWF, NSEP, and the US Navy global models, they all have versions of EDMF. And the figure here, don't spend too much time on that, but it really highlights the fact that when EDMF was implemented at ECMWF, there was a significant improvement in the representation of stratocumulus clouds. And stratocumulus clouds, as you can see on the top figure, that highlights the difference between the new EDMF PBL scheme and the old one, increased by about 30% on these key regions off the west coast of continent. Now, let me just spend the last few minutes talking about slight variations of EDMF that we've been exploring over the last few years in the NCAR model and in the SCREAM model, and I'll show 2 slides of each. So for NCAR, what we've done, NCAR has Club, which is a higher order closure that Chris Golas and Vince Larson and Peter Bogenschutz and a variety of others have developed over the years. And what we did was to merge Club with multiple mass flux plumes and see what would happen. And the idea here is that Club, although trying to represent a skewed part of the distribution, doesn't always necessarily do so. And it also has a tough time doing deep convection. So in a sense, what we're trying to do is to use the great properties of Club representing this sort of double Gaussian mixing. And in a way, it's replacing the eddy diffusivity, but more effectively than eddy diffusivity, of course. But then the mass flux plumes represent sort of an additional discrete skewness that may be necessary to complement the double Gaussian mixing. And the way this is coupled to Club, essentially Club being a high order closure, the equations are solved by a 5-diagonal prognostic solver instead of a 3-diagonal one. And so we add the mass flux plumes on the right-hand side of the solver for the mean variables. And so all of this, the fluxes and the mean fields, are solved simultaneously and are all aware of the mass flux property. And I'll show you just one result. So we did a lot of one-dimensional models, of course, single column. We've done a lot of 3-dimensional work. And this is just one example. This represents a sort of experiment, AMIP experiment that we've run. This is on the left, annual mean precipitation for a period of about 20 years. On the right-hand side is the low cloud cover. On the top, you have the observations. Next, you have Club level 32. This is pretty much CAM6, a slightly different version of CAM6, but it's not too far from CAM6. Club L58 is a slightly different version with different dynamical core and 58 levels, and then Club MF has 58 levels and the different dynamical core as well. And as you can see, I mean, we're not trying to argue that Club MF is better than Club 58, L58, but the main reason to have been very satisfied with these plots and these results is that we are able to represent the key aspects of a global climatology of the atmosphere, and there's many other figures, by using Club MF. And the key aspect of this story that you have to sort of keep in mind when looking at these plots is that we don't have an explicit deep convection scheme in ClubMF. So while Club L32 or L68 have Zhang-McFarlane, there is no deep convection scheme in ClubMF. So ClubMF is actually able to do stable boundary layer, dry convection, shallow convection, and deep convection when necessary, introduce precipitation and all that. Now, let me just spend the last 2 slides on the DOE results. So a lot of work has been going on trying to couple the multiple mass flux plumes with the simplified high order closure scheme that Peter Bogenschutz and Steve Kruger developed. So in this sense, I think this is even a more natural combination than with Club, because shock, being a simplified high order closure, has many characteristics that are relatively similar to an eddy diffusivity turbulent kinetic energy scheme. And by adding the multiple plume MF, we again are adding this sort of additional discrete skewness to the distribution and representing the vertical mixing in sort of shallow convection cases and deep convection cases a bit better than shock. And I'll give you 2 examples. This is from a very nice paper that Maria Shinita has led within our team. This is again the shallow convection, so puffy popcorn clouds. This is mean profiles of the mean liquid water potential temperature, the mean total water, and the cloud fraction. And while you can see small differences, but actually very relevant differences between, on the one hand, LES and the shock MF are very close to each other, and shock is slightly different, and you can see it a little bit on the temperature and the water profiles. You can see the consequences of that much nicer or much better in terms of cloud fraction. And you can see that while shock in the BOMEX case ends up sort of representing a regime that is more akin to stratocumulus, or is somewhere between shallow convection and stratocumulus, that shock MF is able to represent shallow convection better. And the last slide I have before the summary is the work that Maria has been doing, and we're collaborating a lot with Peter Bogenschutz on this one as well. This is the work that she has done using Deep Scream and trying to understand, again, this transition of tropical convection over land, and looking at how the LES reproduces the transition, how shock does, and how shock MF does it. And this figure, you can see how this is a time cross section, and you can see how the LES reproduce the growth of convection and clouds, how shock is actually not completely able to reproduce that growth, and shock MF is much closer to the LES in reproducing that growth. So we're very optimistic that these results are very promising in the work we have ahead of us, and we're very optimistic that we'll be able to contribute to the next version of SCREAM and help the sort of DOE develop a better climate model. So this is my summary. Again, this is work by a lot of people. The DOE work, as I said, is led by Maria, and the NSF work has been led by a lot of us with great contributions from Adam Harrington at NCAR. EDMF is a unified parameterization, blends the eddy diffusivity approach and mass flux, represents well turbulence and convection, has been implemented in global NWP models. We have, for the first time ever, a 3-dimensional global model that has one single unified parameterization for turbulence and convection from PBL and deep convection. And most recently, we've been testing shock MF in the DOE Deep Scream, and we've been able to show positive results for shallow and for the transition to deep convection. Again, thank you for your time, and I'm happy to answer any questions.
Okay, thank you. So I know some people have to drop off at the hour, but if you have a question, you can just speak or raise your hand or put it in the comment.
So I have a question. Thanks, Joao. This is Peter Caldwell. That was a nice talk.
You do?
So when you're implementing MF in say shock, is the basic idea that you are making the mass flux, so kind of the convection scheme, like just a sub-module of shock rather than having it be its own module? So asking kind of practically like how you're implementing it.
Right. So the mass flux part is it's all calculated together with shock. So it's just one sort of algorithm. It's not a separate component that comes later or anything like that. So usually what we've done, the typical approach has been that we go into the boundary layer code of a model, and we calculate the mass flux terms that are required, and then we add the mass flux terms within the numerical solver of the boundary layer. Usually it's a three-diagonal solver for a sort of eddy diffusivity like parameterization. And so all of that is solved together. So the diffusivity, in this case shock, or club, when we do the five-diagonal solver, is aware of the mass flux terms because everything is solved together. So it's just one parameterization, one algorithm that is made a little bit more complex by adding the multiple plumes. But there's nothing added like a Zhang-McFarlane or something similar, which is called before or after the boundary layer.
Right. Okay, thanks.
Is there sensitivity to resolution with, so on the images that you showed, are those all uniform resolution, and is there tuning that's required?
So yes, there is tuning that is required, and I don't think that's different from any other parameterization or model component, right? We always have to tune. The sensitivity to resolution is becoming a much bigger issue because of the fact that we are now with Scream and other models trying to get into sort of unexplored territory of running global models at resolutions of, let's say, 3 kilometers, right? So it's not that EDMF is more sensitive to resolution. ShockMF will be more sensitive to resolution than other schemes. But we are now exploring that sensitivity because we're testing ShockMF with a variety of different resolutions with Deep Scream. So this is work that Maria has been doing over the last few weeks or a couple of months, in which she has been using different resolutions, and the model does behave differently, and the parameterization does behave differently. And so trying to come up with an optimal scale adaptive version of ShockMF is sort of the main goal that we have right now. But we are optimistic that we will be able to do that. But we're sort of encountering problems that are not too dissimilar from what others have encountered when running Scream or global cloud resolving models at resolutions that span from, let's say, 3 kilometers to 25 kilometers, right? So the boundary layer is gonna, or the boundary layer, the parameterization is responding differently because the dynamics is responding differently. So we have to find, and we've done this work in other contexts in which we found solutions for this, but finding the optimal solution for this sort of scale adaptive issue is still something that the community is trying to go after. I don't know if Maria wants to say a few more things about this, but I know she was on the line before. I don't know if she still is.
Thank you. Other questions? Okay. All right. Well, thank you, Zhuang. And
thank you.
Thanks everyone for attending, and we'll see you in a few weeks in Denver.
Thank you, everyone.